Operation Classroom. Today we are discussing temperature sensitivity of Arrhenius reactor. My name is Dr. Chaudhary. The reaction rate constants of two reactions, let's call them 1 and 2, follow Arrhenius law. We all know what Arrhenius law is. The activation energies of reaction 1 and reaction 2 are E1 and E2 respectively, where E1 is less than E2. Assuming same values for the frequency factor for both the reactions, which one of the following statements is correct? Here, we look at the options, but basically we have to find out the comparative temperature sensitivities, temperature sensitivities of reaction 1 and 2 and compare them. Basically, that's what the question asks for. So first we'll see what is temperature sensitivity of a reaction. So we all know this is our Arrhenius reaction. We take the natural log of both sides. So we define ST, which is the fractional temperature sensitivity of the rate constant, as of course taking derivative of this one is equal to E over RT squared. So what is fractional temperature sensitivity? So we know K, let's say K is a function of temperature. So K is a function of temperature. And here, of course, if we increase the temperature by, let's say, 1 degree Celsius, then of course the K also increases. So how much is K changes over 1 degree Celsius? That's a temperature change. Of course, this is supposed to be in absolute temperature. So this dk over dt, that's of course the absolute temperature sensitivity. But here we are finding out d of ln of k. So basically here, instead of k, we are plotting natural log of k as a function of temperature. So what is basically here in this figure, if we take the derivative of that, we are getting the natural log of k over dt. So this is basically, we know, 1 over k dt over dt. So dk over dt. So how much the rate constant changes, how much the rate constant changes per 1 degree Celsius or unit change in temperature divided by the current value of the rate constant. So this is basically the fractional change in rate constant for unit temperature rise. That's basically the temperature sensitivity. That means how much the K value changes per unit temperature rise divided by the current value of K. Okay, so this is almost like a percentage change in K. Okay, so that's basically this one is. So this is my temperature sensitivity. That's the way we define it. So, of course, for the reaction 2, it would be E2 over RT squared, and for reaction 1, it would be E1 over RT squared. And since E1 is less than E2 or E2 is greater than E1, so this is going to be it. So temperature sensitivity of reaction 2 would be greater than the temperature sensitivity of reaction 1. We'll discuss that more later on. So K2 changes by a greater percentage than K1 for the same change in temperature. Okay. So that's a conclusion for E1 less than E2. Let's quickly see difference between this derivative with respect to k and derivative of the natural log of k. We say that derivative of k with respect to t is absolute temperature sensitivity. This is called the absolute temperature sensitivity of k. So this is the actual increase in k per unit Kelvin rise in temperature. Whereas this, we take the natural log of this one, so this is equal to this. So this is a fractional temperature sensitivity of k. And so it can, if you multiply this by 100, of course, this can be expressed as a percentage change in K per unit Kelvin rise in temperature. Okay, so we're basically defining this temperature sensitivity based on this natural law. Okay, so based on this natural change in sensitivity with respect to natural law of K. Okay. So let's look at the options. It says reaction 1 and reaction 2 are less temperature sensitivity at lower temperature than higher temperature. So we define the fractional temperature sensitivity as the derivative with respect to natural log of K, which is equal to this. But that is also so if we take this the temperature sensitivity with respect to temperature, So that also changes with temperature. Sometimes it's much more sensitive at lower temperature. That means it changes, this sensitivity changes very high at lower temperature compared to higher temperature. So how do you find out that? For that, again, let's take the derivative of this one. So we find out derivative of this one. So if we take the derivative, then of course this becomes equal to this. So these all details are shown in this particular website. Since E, R, and temperature are all positive, so this basically temperature sensitivity of or the derivative of the temperature sensitivity is of course always going to be negative. So that means ST decreases with rise in temperature. So temperature sensitivity of anyone will decrease with the rise in temperature. Both reaction and reaction to are more temperature sensitive at lower temperature than at higher temperature. This option says less temperature sensitive at lower temperature, which is not true. This is more sensitive. So this option is false. Let's look at option 2. Reaction 1 and 2 have the same temperature sensitivity. Have seen that since T1 is less than H2. So this is basically temperature sensitivity of reaction 2. This is, of course, temperature sensitivity of reaction 1. Since E1 is less than T2, so we know that they are going to be different. So this is also false. Let's look at option C. Reaction 1 is more temperature sensitive. We see FC. This is ST2, which is the temperature sensitivity of reaction 2. And this is the temperature sensitivity of reaction 1. So since E1 is less than 2, so temperature sensitivity of reaction 2 will be always greater than the temperature sensitivity of reaction 1. So this option D is true. Option C is, of course, false. So this option D is the correct option. Another just note that the problem states that the frequency factor A for two reactions 1 and 2 may be assumed equal. So if we look at the problem statement here, it says that we can assume the same value for the frequency factor for both the reactions. Now, we have not really considered the frequency factor in our entire arguments. So let's see how and what difference it makes. So in our problem, we have defined the temperature sensitivity as E over RT squared, and as you see, the value of E is not there. So our analysis is based on temperature sensitivity defined as relative or fractional temperature sensitivity, which is basically taking the derivative with respect to natural log of K. If we had taken the absolute value of K, then we know this absolute value of K being K, being of this one, because this is nothing but 1 by K, dt over dt. So if you multiply this by K, this cancels out. So this is dt over dt, this one right here. So that is equal to this expression here, which is a little complicated. We have not considered that. If we assume relative or fractional temperature sensitivity, which is the derivative with respect to natural log of K, so we can say even for if A1 is not equal to A2, option D is still the correct option. So it does not matter. Let's look at a practical application of this problem. Ethylene oxide is produced by catalytic oxidation of ethylene over supported silver catalyst. We know that. The temperature is approximately 460 to 500 Kelvin operating temperature, 17 bar absolute, and it takes in presence of 2.5 ppm of dichloroethylene. Two important reactions. One is a desired epoxidation reaction where ethylene oxide is produced. This is the desired reaction, and this is the activation regime. And another is the undesired combustion reaction where carbon dioxide is produced. This is the undesired reaction, and the activation is pretty high, 160.5 kilojoule per mole. So if we define as ST is equal to E over R2 squared, what we have seen before, at 480 Kelvin, if we do the calculation, we see this is the value of temperature sensitivity per unit Kelvin, and this is 0.08 T per unit Kelvin. So let's call this as an apparent activation because a lot of things depends upon the catalyst, pores, catalyst active sites, operating pressure, etc. So let's call this as an apparent activation energy here. Okay. So as you can see, temperature sensitivity of reaction 1, which is a desired reaction, is much lower than the temperature sensitivity of reaction 2. So for unit degree Celsius rising temperature, this value of K, this rate of reaction change is much faster than the value of K or the rate of reaction 1, which is the desired reaction. Okay. So as you can see, temperature sensitivity of 2, which is the undesired one, is higher than the desired one by 1.70, which is almost 70% higher of temperature. So you have to be very careful in designing the temperature control of the reactor. Let's take an actual example. Let's say we increase the reactor temperature by 10 degrees Celsius, which is of course equal to 10 Kelvin, difference in temperature. Let's assume we change it by from 480 to 490 Kelvin. We know that the value of K changes by this reaction. It's another form of Arrhenius equation. So the value of K at 490 Kelvin would be 63.2% higher than the K1 at 480 Kelvin. And similar calculations for reaction 2 will show you that K2 at 490 Kelvin, remember this is for the undesired reaction, is 137% higher, just for the same 10 degrees Celsius temperature rise than K2. Here it is only 62% and here it is 127%. So undesired reaction has a much higher temperature sensitivity and higher effect. So a temperature rise of 10 Kelvin increases the combustion to oxidation rate constant or rate reaction by almost 40%. So that has to be very taken carefully taken care of while designing the reactor. Anyway, finally, so as we say, option D is of this option D is the correct option.